Welcome to Monday Night Calculus, October 2nd, 2023. My name is Curtis Brown. I'm really excited for all of you to be joining us here this evening. I am joined once again by Steve Kokoska and Tom Dick. Really excited to have these two guys here, these experts in calculus here to share their knowledge. I will be sitting off to the side. I did not do my homework tonight, Steve, so I apologize for that. You can certainly ask me any question that you should so choose, and I will just defer to the chat and hope that we've got some students and teachers ready to go. We've got a few people on the chat tonight already. I see Jude and Dawn, both people mentioning that they are ready to go. No place they'd rather be on a Monday night. I can't believe it. They're not even out watching the Manning brothers. Well, I can't speak for that. They could be also watching the Manning brothers here shortly. So, but anyway, I will quit talking and I'll let you guys get started. I'll keep the chat going and we'll give some information as we go.
All right. Thank you, Curtis. I'm going to share my screen. I hope that's up there. One quick question before I get going, Curtis. Is Taylor Swift on tonight?
No.
No. Okay. Just checking. Okay. All right, well, we're going to do a little something a little different this evening. I'm going to start out with a couple of reminders. And when I finish that, Tom is actually going to do a little technology, and then we'll take a look at some of the problems that we assigned for homework this week. So we're going to talk about differentiability and local linearity tonight. And the first thing I want to remind you of is our strict definition of the derivative of a function at a number a. Now, this is the definition that I generally use in my class, that I start out with in my class. I don't know why, but I find this one easier to illustrate, just easier to look at geometrically. And I don't know why. I find the notation there just a little bit easier for my students. But don't forget, there is this, what I would call alternate definition of a derivative, which is another limit, which I will use tonight, I hope. And that would be the limit as x goes to a of f of x minus f of a divided by x minus a. Now, I often get this question about, well, if I have to find the derivative function or the derivative of a function at a value, which of these definitions should I use? And I don't have a good answer for that. That takes a lot of, I think, calculus vision, a lot of experience, a lot of solving problems, so that when you see a new one, you know that it makes sense to use one of these definitions over the other one. So, okay, a function is differentiable at a value a, if, of course, this limit exists. Well, all right, what does the graph of this function look like if it's differentiable at a point a, f of a? Well, the graph of f would then be smooth. That means that it has a tangent line at that point. Tom would have to help me on this one, but I think I remember that this word smooth is used more commonly in upper level, higher level mathematics. What does that mean for us in calculus? Well, if we draw the graph, there's no sharp corner or there's no cusp. The graph doesn't change direction abruptly or sharply. And yes, I know we have seen lots of funny words or phrases to this sharp corner or cusp, but I'd like to suggest that students, teachers, stick to those two phrases, a sharp corner or cusp. We understand what those mean when we read them on the AP exam. So, okay, let's suppose that f is differentiable at a value a. Geometrically, that means if we continue to zoom in, get closer and closer to that point a, f of a, then the graph of y equal f of x really looks like a straight line near that point. And that's this property that we refer to as local linearity. I think I remember that phrase first coming into vogue with TI-Cap and the advent of technology. This whole idea of local linearity that we could actually see on a graphing calculator. So, okay, what does that really mean? If we have local linearity, if we have differentiability at a value a, well, then that means that, think about this visually, that means that the tangent line to the graph of f at that point is really a pretty good approximation near A. If near that point the graph looks like a tangent line, looks like a straight line, the tangent line ought to be a good approximation. Cool. I'm going to turn it over to Tom for one quick demonstration, and then I'm going to take a look at some problems for tonight. Tom, all yours.
Okay, thanks, Steve. All right, I'm gonna try to share my screen here. See if I can pull up just kind of a quick calculator illustration here. So I pulled up a TI-84. I hope you all are seeing that. I'm just gonna jump into a graph here. Oh, here we go. So here's a nice graph. I'm going to put you on the spot, Curtis. Are you ready? All right. I've done no funny business here with the scaling. The scale on the X and the Y are the same. It's like a zoom decimal window. So you had to guess what that graph was, what the function was. What would you say? I think you're on mute.
I'm on mute. It looks pretty close to something like y equals x. Maybe it's a little steeper than y equals x. So maybe I'll say y equals 1.3x.
All right. Yeah. Well, actually, your
definitely goes through the origin there, and it appears to have a slope of 1 or very close to 1.
Yeah.
On the screen you've got there.
Yeah, I agree. To you too, Steve. And so
yeah, sure looks like y equals x to me.
Okay. Well,
But I know you better than that, Tom.
I'm going to trace it just to see, but you know what? The trace is probably going to let the cat out of the bag.
Oh,
it's sine x.
Wait a minute. I've never seen sine x look like that before.
And if I just trace a little bit, you might be able to gather what's going on there. Let's see. You can see that the increment on x is very tiny.
Oh, you're zoomed in super tight.
Exactly.
Hey, Tom, I got to tell you a little trick right here, just for teachers out here who want to do this investigation with students or put them on the spot for this later, which I know it's being recorded for posterity. And so I'm going to hide this. Why you can actually turn off when you press trace, you can turn that expression off. You can make sure it doesn't show.
Oh, really?
You can. Press the second and the zoom key to get to the format screen.
Okay.
We'll just pause here for a second just for teachers to see this. So if you go down to about the fourth one up from the bottom where it says expression on, expression off.
Oh,
if you turn that expression off. And I see, by the way, that we've got Don is saying, I swear y equals x goes corner to corner on a standard window, so it couldn't be y equals x. However, the window is changed. And so Don Breaker caught us on that. But yeah, now if you hit trace, you'll just get a little Y3 over there.
Oh man, good. I wish I had known this years ago out there. This is nice.
You can hide that.
Because now tracing, if you thought it was y equal x, this would not dissuade you at all.
That's correct.
Because those y values looking pretty similar to the x values.
Yes, those look exactly the same. So now I'm back to y equals x.
Now I've gone just far enough that maybe we're thinking something's going on. Notice that the y value is not quite the same as the x value. Well, I'm going to actually trace back to the origin. And I'm going to do a zoom out. So I'll go down to 3. And what Steve just mentioned was if you zoom in on the graph of a differentiable function, it should straighten out. I'd already done that. So I'm going to kind of reverse that and zoom out. And I'll do that repeatedly. And each time I zoom out, now we get a little bit better sense that, yes, it was indeed the sine function I was looking at. But just a quick anecdote. One of the very first workshops I did with teachers, literally, is 30 some years ago, with calculators. We were playing around with zooming in and doing various window changes. And one of the teachers said, "Oh, I zoomed in so much on this graph, it ended up looking straight." And the teacher paused for a second and then suddenly said, "That's significant, isn't it?" And indeed it is. There's a mathematician named David Tall. He got a PhD in both math and mathematics education. He claims that this is maybe he calls this a cognitive root for calculus. This notion that a differentiable function has a graph that's locally straight is profound and really important. And we can just milk that for a lot of meaning, a lot of insight into why differentiable functions are so special. So I will jump off my soapbox there and hand it back to Steve, so he can dive into the problems here. Oops, let's see. I want to stop the share. And let's.
How about that?
There we go. Okay.
Got that? All right, Curtis, this is one of my favorite problems about differentiability and local linearity. I like this one a lot. It's got a couple of parts, and I hope you've done your homework on this one. I might have some questions for you. Here are a couple of functions. F of x is equal to the absolute value of x. We know an awful lot about that one. Tom and I were talking about this on Saturday, or last Thursday, excuse me, with AP Pre-Calculus, that the two most important ideas in mathematics are that of a function and the definition of absolute value. So one of the most important functions in mathematics. And here's another kind of crazy one. G of x is the square root of that x squared plus 0.0001 and then minus 0.01. So the very first thing that I know you thought about, Curtis, was what is the domain of those two functions? Because they look a little strange. Maybe the second one does. So I'll help you a little bit. The domain of the absolute value function is all reals, but what about the domain of G? Do we have any problems there at all? Is there anything we need to worry about? Is there any possibility that underneath that radical symbol we could have a negative value?
No.
Good, very good. Say that with a little bit more confident.
Possibility there.
Right, because x
I don't
squared
even see a possibility of 0.
Very good. Excellent. So the domain for both of these functions is all real numbers. So the first thing that I asked you to do for homework was to graph both f and g in the same viewing window. And in fact, I gave you a viewing window to try, which was -5 to 5 and 0 to 5. I just want to remind you that I think this is our pretty standard notation for a viewing window. And a lot of my screen illustrations, as Curtis and Tom know, I usually use the TI-Nspire. Tom will show you some of this similar screens with the TI-84. But I do a lot of stuff with the TI-Nspire, and I do a lot of graphing with Mathematica. So this is with the Nspire. And if you look closely at that, boy, it sure looks like there's only one graph there. In fact, in this viewing window, it looks like these two graphs are essentially the same, which is crazy. So that begs, I think, the next part of this question is, well, you know what? Let's take a look at a table of values. And I cheated a little bit here. I recognize that both of these functions have some symmetry about the y-axis. So rather than create two separate tables, for my x values, I did plus or minus 1.9.8 because I could see the symmetry. I know about the absolute value, and I know that that second function g is also symmetric about the y-axis. It's an even function. So here's some values that I got. The absolute value here, f of x, well, that's pretty easy. And here are the values I got with g of x using my TI-Nspire or Mathematica or other technology. And what do you notice about this table? Well, boy, those values are really close. But there's a couple of things that I notice. It seems like the value of g is just a little bit smaller than the value of f. And in fact, if I look at them even more closely, it looks like they differ by about 0.01. That's kind of weird. That was that value on the end. Well, except that x equals 0, of course. So let's try this one. In C, what I wanted to do was to zoom in more on both of these graphs, f and g, zoom in near the origin. And what do you notice now? Well, look what happens. I suspect that many of you, many of the teachers who are listening, and some of the students have seen this before, where we zoom in over and over and over again on that absolute value function. And we can't get rid of that sharp corner. In other words, we can't make it flatten out. We can't make it look locally linear. But look at that function g. This does seem to support what we saw in the table on the previous page. Its values seem to be less than the corresponding values of f. But look at what's going on with g near the origin. Even though f has a sharp corner or a cusp there, boy, it sure looks like g is nice and smooth at that 0.00 at the origin. Okay. So
I've got a comment in the chat talking about a cusp.
Yeah.
Sharp edge called a cusp.
Yep, we can use that phrase. I think we understand that one. Yep. So part D says, well, let's see if we can evaluate f prime of 0 or explain why it doesn't exist. Well, just by looking at the graph, as someone just commented in the chat, there is a sharp edge or a corner there or a cusp there. So that suggests geometrically that the derivative does not exist there. It's not smooth. How do you show this analytically? I'm going to scribble a little bit here on the side if I can. Let's suppose I wanted to take a look at the derivative of f at 0. I'd have to, one limit I can take a look at is the limit as h goes to 0 of f of 0 plus h minus f of 0, all of that divided by h. I'm going to make one more step and then I've got a question for you, Curtis. This is the limit as h goes to 0. Well, what's f of 0 plus h? That's just f of h, which is the absolute value of h. And f of 0 is 0, and I've got an h down here. How do I evaluate that limit? This is one that many textbooks have. Many teachers, I think, do this one in class. It's not that bad. How do you evaluate this limit? How do you support analytically that this derivative at 0 does not exist? How do you evaluate? What's the general technique? Sorry, Curtis, I'm putting you on the spot there.
You really are putting me on the spot, and
Sorry.
There's enough of a delay in our video here that me just jabbering for a second till the students
might get an
answer this.
Okay.
Might not do the thing. Mostly I'm kind of doing that just so Wanda will step in and help me out, or Alex, who has just joined us here this evening, who's saying that he's a living proof of success on the AP exam, which is great.
Oh, good.
But I approaching by left and right hand sides of 0 and checking to see if the values approach the same.
Very good.
Value is
excellent.
Kind of the way that you would go with that.
Excellent.
I wanted to make sure that we had plenty of opportunity for that to get to the chat.
Very good. Indeed, in order to solve this one, you have to take a look at two one-sided limits, and you'll find that those two one-sided limits do exist, but they converge to different values, so the overall limit does not exist. Very good. So we've seen it graphically. We can do it analytically, or we've seen it analytically. Let's go back to g, the function g for just a minute. Now, this looks horrible. but sometimes you just got to do some of this analytical stuff because it's cool. So I'm going to see if I can find a general expression to the derivative of g. And then I'm going to use that expression to find the derivative of g at 0. So I don't know if there are many of these problems on the multiple choice portion of the exam where a student would actually have to use the definition in order to find a derivative. I don't think so. But there are some of these problems where you actually have to work backwards. And that is where you're given some sort of an expression, a limit expression, and you have to recognize that it is the derivative of a function at a value. So knowing this definition, being able to manipulate limits with this definition is still, I think, a very important skill. So here we go. I'm going to use this first definition of a limit. I'm going to plug in g, evaluate g at x plus h and just x. And I'm going to use this technique where I multiply what I call multiply by 1 in a convenient form. In some sense, I'm kind of rationalizing the numerator. And so if I've done everything correctly, I get rid of the square roots up there in the numerator. I can do a little simplifying. These decimals will cancel. In the next step, the x squareds cancel. You'll notice I can factor out an h now. That'll cancel. And some really good things happen here towards the bottom. See if I can arrow up a little. So right here, I think I can now evaluate this limit. And I can evaluate this limit by direct substitution because I no longer have a 0 in the denominator. I've gotten rid of, in some sense, that product, that factor h in the denominator. So if I use direct substitution, it simplifies to this expression. I can get rid of the 2's. And here's my general expression for the derivative of g at any value x. And in fact, this is really easy now. If I plug in a 0 for x, I get back 0. That says the derivative of that function g at 0 is 0. The slope of the tangent line is 0. So Curtis, what's an expression for the tangent line to the graph of g at 0? What would it be?
Wait a minute.
Just, you're correct. Y equals 0. Very good. Excellent. It would be right on the x-axis. You're really quick tonight, Curtis. I'm impressed. Very good. Excellent. I like that problem a lot. There's a lot of neat things going on in there. I could see it graphically. You know, we start out by saying those two functions look very similar. One has a derivative of 0, one doesn't. And there's some nice skills in here about actually finding the derivative by definition. Cool. Tom, you want to take a look at a little bit of technology before I get to number 2?
Couldn't remember if you were talking about if f was the absolute value or g was. That's
Okay.
why I missed on that.
Sure, Steve. I'd be happy to take a look at some.
All right. Little technology. I'll come back to those problems.
Okay. All right. I'm actually going to go back to the 84 again.
Okay.
And bring up my screen here.
Hey, Tom, while you're doing that, I did get a question from Wanda about whoever it was that you mentioned in your earlier example.
The person's name is David Tall, Tall. He's a real giant in math ed.
I see what you did there.
You know, that was unintentional, Chris. All right. Okay. So
even better.
All right. So I just thought it'd be nice to look at this same two functions Steve was looking at, but go ahead and do this dynamic zooming. So Steve showed some successive screenshots of zooming, but let's kind of see what that looks like. And just for grins, you can see that I've already entered in for y1 the absolute value of x, and for y2 is which was our f of x, And this is that g of x function, which is this kind of funny square root thing. And I think I'm figuring out that Steve orchestrated that. So when you plugged in 0, let's see, square root of 0.0001 would be 0.01. And so when you subtract off the 0.01, you end up right at 0, 0, just like you do on the graph of absolute value of x. Now, down here on Y3, let me go ahead and activate these for graphing. So I'm just selecting Y1. I'll select Y2. And just for grins, I'm going to throw in a third function. It won't be sine x. We already took a look at that. But the graph I'm going to put in here is going to be x. It's also going to have go through the origin. Its graph will go through the origin. That's x to the 2/3 power. Okay. Now, let's just go ahead and graph all three of these and see what they look like. So I'm going to do a zoom decimal window. That's kind of my favorite window in calculus because it has that equal scaling both in x and y, and it gives me some nice pixel values. And there's the absolute value. Well, there's the g of x, which just covers it up exactly. And now here's this y equal x to the 2/3. Now you might be thinking, why in the world am I looking at this? Well, it's something I wanted to acknowledge that, my own sense is I'm hoping we don't go there on the AP exam, but I want to acknowledge that there's some books will make a kind of a technical difference between a cusp and a corner. So a cusp in many books, they reserve that for a function. It has a sharp change in direction, but it's super sharp, meaning that the slopes are approaching positive infinity as you approach from one side, and the slopes are approaching negative infinity as you approach from the other side. And we're going to, here it looks like x to the 2/3 has maybe just a slightly sharper corner than absolute value does. Let's zoom in and see what happens. So let me go down to zoom in. And what's nice about the zoom capabilities is once you've selected one, if you want to just keep doing it over and over again, you just can, all you have to do is hit enter repeatedly. Okay, so here's one zoom in. And now we see a little bit of more sharpness there to that x to the 2/3. We're not seeing that rounding out though yet because we haven't zoomed in enough. You can kind of tell we've zoomed just looking at that the hash marks and the axes are not now further apart. So let me zoom in again. Oops, let me do that. Should have just hit enter. So, okay, here we go. Here's a second zoom in. And now we're seeing that red graph. That's my g of x graph. It's starting to round up a little bit at the origin, but you can see that the x to the 2/3 really getting a sense of that cusp behavior. And I think on the purposes of the AP exam, I mean, the recognition they're going to be looking for is that students should know that if a graph has either a sharp corner or cusp, that's going to be a violation of it being differentiable there. That will be the key thing. So here, in fact, if we zoom in one more time, now we're seeing a very flattening out of my g of x graph, the red one. The absolute value graph, it just remains unchanged. You can zoom in until the cows come home. It's still going to have that, look like it has a right angle there. And we can see just how sharp that cusp is on the x to the 2/3. So kind of rehashing, but just kind of illustrate, I think the dynamic zooming that you can do with technology is just a really powerful visualization tool, especially in this context of local linearity and differentiability. All right, Steve, I'm going to turn it back to you so you can.
All righty, thank you. Well, let's see what we can do with some of these other problems. Okay, so given what we've talked about already, and given some of the demonstrations that Tom has shown us,
a typical sort of problem is just, let's take a look at some graphs and recognize whether a function is differentiable at certain points where it isn't differentiable. So let's take a look at these two functions, graphs of these two functions in A and B, and let's determine where the function is not differentiable. Okay, pretty straightforward, especially given what we've talked about this evening, but let's knock these off. For A, this is a graph of this function f. It's certainly not differentiable at x equal -3. Heck, it's not even continuous there. Remember that if a function is differentiable at a value, it must be continuous. That's a theorem. We can see the hole in that graph, and so it's definitely not differentiable there. It's also not differentiable at x equal 2. There's this sharp corner there. I'm not quite sure in Tom's lingo if there's actually a cusp there, but there's a sharp edge or a sharp corner. It's not differentiable there. And how about in B? Well, I think there's 3 places we need to worry about. Little different, but we have a sharp edge or a sharp corner right there and right there, so it's not differentiable at -3 and 3, and it's not continuous at x equal to 1, so it's not differentiable there. So pretty straightforward, but I think good exercises to make sure that students can recognize where a graph is differentiable, where it isn't. Very good. All right, I got a couple of other problems here for homework that you've been working on. This is a nice one, I think. A lot of these problems involve the absolute value function. Let's take a look at f equal to x times the absolute value of x. I remember my college calculus teacher telling me, in calculus, whenever you get a problem that involves an absolute value, one of the things you have to do is to work to somehow get rid of it. Somehow rewrite the function, rewrite the expression without that absolute value. And so that's what I tried. So I'm going to rewrite this function because I know the definition of absolute value. If x is greater than or equal to 0, the absolute value of x is x. So this function just becomes x times x, or x squared. And if x is less than 0, this function f becomes x times minus x. So that's a way to write this function as, well, a piecewise function or piecewise defined function. Well, from there, it's pretty easy to graph. I believe you could actually graph this with technology on the 84 or the Nspire, either this way or typing in the original, but there it is. And you know what I'm interested in. I'd like to know what's going on with this function near 0. Is it differentiable there? So for what values of x is f differentiable? Well, let's see if we can answer some of this. And yeah, Curtis, sorry, there's another question coming up here.
Sounds good.
All right, for f of x for x greater than 0, greater than or equal to 0, we know that f is equal to x squared. Okay, we've been talking about the definition of the derivative tonight, but maybe we're at that point in the class where we know a couple of differentiation rules. We know the power rule. So we know the derivative of f is equal to 2x as long as x is strictly greater than 0. Wait a minute. Why does it have to be strictly greater than 0? Why can't we go all the way up to equal 0, I wonder?
I would have to do with that endpoint definition, right? That you
Well, you're on the right track. You're on the right track. So the definition of derivative, the definition implies that the function is defined in what I call a neighborhood.
Yeah, you
Right?
have a closed bound. You'd need an open bound for that definition, right?
You need an open interval because if you think about that limit, we've got to be able to come from the right and the left. And we can't do that if we're at an endpoint. So we know the derivative for x greater than 0 is 2x. For less than 0, it's minus 2x. And so now the question is, what's going on near 0? Or at 0, excuse me. Well, at x equals 0, I'm going to go back to the definition of the derivative. And just for a little variety, I'm going to use that alternate definition. So that would be the limit as x goes to 0 of f of x minus f of 0 over x minus 0. There's f of x. F of 0 was 0. The x's cancel, And this limit is pretty easy. That's the limit as x goes to 0, the absolute value, which is 0. Therefore, it turns out that this function is indeed differentiable at 0. And its derivative there is 0, son of a gun. So, can we put all of this together? Can we get a formula for f prime? It turns out that indeed you can. It turns out that the derivative f prime can be written like this piecewise right here, 2x if x is greater than or equal to 0, because for x greater than 0, we already showed there's the derivative, and if it's equal 0, the derivative is 0, so that works. 2 times 0 is 0. And less than 0, there's the derivative. And thinking about this just a little bit, another way to write this with a single formula, not piecewise defined, is 2 times the absolute value of x. Now that might not look right because I see a -2 out in front. So I'm going to let you think about that just a little bit. How does that all reconcile? It does. Now, one thing that I did not do, but I think would be a nice exercise with your students tomorrow morning at 8 o'clock, is to graph both this function f and its derivative to make sure that you can see this relationship about increasing and decreasing if you're that far enough along in the curriculum.
So
That's the next problem.
I got a good question from Don here in the chat. Would it work if we put the equal on the less than side because it's 0 anyway?
Sure.
Seems
That would
like
be
that's
okay.
a reasonable statement, right? You drop
Sure.
that. You could have it
Yeah.
on either one.
You can have it on either one. Yeah. Good question. Was that Dawn or Donna that asked that?
Well, I'm going off of the YouTube name, so I'm going with
Okay.
Don.
Okay. All right, here's another one, Curtis, that involves the absolute value. This is g of x is equal to x plus the absolute value of x. And once again, what I'm going to try to do is to get rid of that absolute value, to write an expression for this function g that does not involve an absolute value. And let's see, does this work? Well, there's the definition of the absolute value. So if x is less than 0, the absolute value of x is the opposite of x, so it'll all cancel out and give me 0. If x is greater than or equal to 0, the absolute value of an argument is the argument. So I'm going to be left with 2x. So there's a piecewise defined expression for this function g. And it might be easier to see this graph by looking at that piecewise definition. To the left of 0, the function graph is right on the x-axis. And then at 0, it changes and becomes this straight line segment, y equal 2x. Pretty cool. Well, for what values of x is g differentiable? Well, given what we've talked about this evening, there is a sharp edge or a corner only here at x equals 0, right at the origin. There's a corner there. So it turns out that this function g is differentiable everywhere except at 0. So this is kind of a cool one. Here's a way to represent the values where it is differentiable. And in fact, you can find a formula, I think, for this derivative. If this is g, here's a formula for the derivative. Notice 0 is not included in here. And we can also see that by looking at the graph, right? What's the slope of the tangent line to the left of 0? It's 0. What's the slope of the tangent line to the right of 0? It's 2. And just to get a little bit more in here, a couple other concepts in here, another function. I think a way to write this without piecewise defined notation is 1 plus the sine of x, not sin, but sgn, the sine function. Do you know what the sine function is, Curtis?
I
Do you
mean,
remember that one?
hold on.
Okay, no looking it up, no phoning a friend here.
I mean, it's a function that returns just the sign. of the value.
Well, it doesn't return a sign like a positive sign or a negative sign, but it is dependent upon the sign of the value. You're right there. If the sign of the argument is negative, it returns a 0. And if the sign is positive, it returns a 1.
That's just a piece.
I think it was, pardon me, returns a minus
I mean, I
1.
suppose you just do a piecewise defined function for x is less than 0. You return 0.
-1, -1.
Yeah, and for x is greater than or equal to 0, you return a 1.
Very good. Excellent. Excellent, Curtis.
I like
All right,
that.
we're on a roll. See if you get this one. Whoops.
Boy, I don't know.
Yeah, all right, let's see. I like this one a lot. Gonna have to look at a graph of this when we get through all the analytics here. Let me see if I can arrow up just a little bit. There we go. So here I have 3 different functions. I have f, which is, let's see, x minus 1 squared. So it's a quadratic. I have a function g, which is an exponential, not too bad. The exponent there is minus 2x. And I have h, which has got a log function in it. Holy Toledo. So I won't read through all of this with you, but what I'd like to do is to find an equation of the tangent line to each of these graphs at the point where x is equal to 0. So naively, just thinking about this, I'm going to come up with 3 different equations. But let's see what happens here. I'm going to take a look at the function f first. That's above this line. What's my point? I need a point, remember, and a slope. So let's see. If f of 0 is equal to 1, so there's the point that it goes through. And what's the derivative? Okay, I'm probably skipping ahead just a little bit. I'm actually taking the derivative here by using the chain rule. But many of you are at this point in the class. If you're not, you could, in fact, expand out that quadratic and take a derivative. That's okay too, term by term. If I do that, I get a derivative of minus 2. So that's my slope of the tangent line. Here's my point slope formula. And I'm going to rewrite that just a little bit as y equal minus 2x plus 1. There's the equation of the tangent line to the graph of f at the point 0, 1. And while we hear Tom and I frequently, Curtis, talk about the AP exam and what students have to write on there in order to receive full credit, and one question Tom and I often get is, well, if you have to report the equation of a tangent line, can you leave it like that, or do you have to write it like that, say in y equal mx plus b format? In general, if you're asked for the equation of a tangent line, this is fine. You don't have to simplify or rewrite that. In fact, if you do try to simplify and you make a mistake, then you will not earn that tangent line point for simplifying and making an error.
Right.
Here's one other question that we frequently get in this case. What if a student writes the equation of the tangent line like this? Is that okay? You can kind of see what I did there, kind of divide by that x, but some students think of it this way because they think of the slope minus 2, change in y divided by change in x. They think of it this way. Is it okay to write the equation of the tangent line that way?
Well, if you're asking me directly, yes. I'm pretty uncomfortable with that. I'm not a reader, but I'm uncomfortable with that because you're left with a division by 0 problem.
Very good. Excellent.
And that gives you a problem.
Yep.
And Wanda's backing me up that you have a domain issue. The domain doesn't match, and so we've got a problem. And Don, yes, to go ahead and celebrate that you do not have to convert from point slope form to slope intercept.
Very
form.
good.
You do not need to carry out that algebra. That's a good thing.
And in fact, I think, Tom, correct me if I'm wrong, but this came up in one of our pre-calculus, AP pre-calculus discussions. was emphasizing that the definition of a function is really two parts. It's not only the equation, but it's also the domain.
Right.
These
Right.
two expressions are not the same. Okay, very good.
Right.
All right, let's take a look at this function g. Well, son of a gun, that goes through the same point, 0, 1. I took a look at g of 0, that's e to the 0 of 1. And I found the derivative of g. Okay, I've got to use the chain rule there, okay? The derivative of that exponential is e to the stuff times the derivative of that stuff. That's just a -2. And so I'm going to evaluate that at 0. And holy Toledo, I get a -2 again. That's got the same slope. And you know what's coming here. This results in the exact same equation of the tangent line to the graph of g at that point. Boy, could that happen for a third one? Let's see. H of 0, well, I plug in a 0 here. I've got the log of 1, which is 0. So son of a gun, it goes through 0, 1. How do you take the derivative of this? Well, term by term, the derivative of 1 is 0. The derivative of that log function, remember, is the derivative of the argument divided by the argument. So there it is. I plug in a 0. Wow, there it is again. Same slope, same tangent line. Now, this might lead some to believe the following. Look, I have 3 functions up there with 3 very different looking formulas. They all go through the point 0, 1, and they all have the exact same tangent line at that point. You might think, correctly, but you might think that in some weird way, these 3 functions are actually the same. But not so fast, Curtis. Let's take a look at these graphs.
We're talking about the derivative or the tangent line at a particular point.
Correct.
Not the tangent function.
Very good. Excellent. So what I try to do, and if you can see this on your screen, Curtis, I tried to do it in color, and I think you can see those 3 functions, those 3 graphs. The curve or the straight line, the tangent line to those 3 curves is in black. That's the graph of y equal -2x plus 1. And now you got to think a little bit, and you might disagree with some of my answers down there. It says, for which function is the linear approximation the best and which is it the worst? And Tom may have a good answer for this one using technology, I'm not sure. But what do you think initially here? Which function do you think that tangent line is the best approximation to? In other words, if we zoomed in over and over again, which of those functions looks most like that straight line, maybe for the greatest interval of x? Which one looks best, do you think?
So which one is the most locally linear?
Well, I don't know if I could use that phrase, but that's not bad. I like that.
I mean, I'm trying to come up with what you're asking there, Steve.
So which of those functions is that straight line the best approximation over the largest interval?
Whichever one has the least steep concavity.
Oh my gosh, I have no idea if that's right.
Huh?
Look at my graph. Look at my graph. Look at that. Yes, sir.
The blue one.
Yeah, thank you. Thank you, Curtis.
Can we look at it empirically?
That was like pulling teeth. We could look at it with a table. We could look at it with a table. That's a great
How about
idea.
looking at it empirically graphically?
Absolutely. Would you like to do that?
I would love to do that.
Okay. Here we go. Boy, took a long time to get there, but okay, here we go.
I mean, I was just, I was trying to come up with something.
I
You
appreciate
asked the question, not me.
it. Okay.
All right. So here's a 84 again, and I'm going to go to y equals. And there's those 3 functions that Steve was talking about. I'm going to add a 4th one because of what Steve's additional question that he posed there, which was, well, let me get to y4. I'm going to put the tangent line equation in there. So that's
Yep,
minus
sweet.
2x plus 1. Now, I just want to be clear, and Steve basically said this. I mean, that's the best linear approximation at x equals 0 for all three of these functions.
That is correct.
Which means if we zoom in repeatedly, all three of those functions are going to approach. They're going to look more and more like that tangent line.
Yep.
Steve kind of raised this second question about, well, which of those functions is that a good linear approximation for the largest interval? Okay, so let's just kind of check that out empirically by graphing all three functions and the tangent line. So the three functions, the blue one is the quadratic, the first one.
Okay.
Red one is the e to the negative 2x.
Okay.
The black one is the one involving natural logarithm. And notice it truncates at x equal 1/2.
Correct.
That you think about why that is. But that's not a concern because we're
Actually,
interested at x equals 0.
so
Maybe not at x equal 1/2. I'd have to take a look at it.
So Tom, I would just you glossed over that just a minute, but I'm gonna point out to some folks why that actually is, and the reasoning is around how the 84 actually makes a plot, right? That it plots pixel points, right? It
Well,
doesn't
in this
just
case,
stop.
Curtis, the domain does end right here.
Oh, it does?
Yeah, because
Right,
it's
I
a
wasn't
natural
paying that
log
close
of the
attention.
quantity 1 minus 2x.
Right.
So when x hits 1/2,
Oh, yeah.
we hit 0.
See?
It's undefined.
I'm glad I put that out there so that the students in the chat and the teachers in the chat could, see that and hear that explanation, make sure that we got that out there. I asked that question on purpose.
Gotcha. All right. Well, I'm going to cursor up, not by trace. I'm just going to cursor up until I hit 0, 1. Okay, there we are. And the reason I do that is now when I zoom in, that's going to be the new center of the screen. So we'll center our attention right there. So let's do a zoom in. And as I mentioned before, once you do this once, we'll be able to do it repeatedly. Okay, there's our quadratic, there's the exponential, the logarithm, there's the tangent line. And so it's like the magenta line is the tangent line. Is which one is it is keeping close to that the longest? What did you decide, Steve?
It sure looks like the blue one. I mean,
I'm getting I heard one person quote that they said they think the square, the one with the
quadratic, yeah.
Yeah, the blue one looks like
it's
it's
the
staying
best.
closer. In fact, we could say which one will be the first to be indistinguishable from the tangent line. Well, I'm going to say this: I can't see blue anymore.
I definitely can't
Because
see
it's
blue.
totally
I do see
covered
the black
up.
a little
So,
bit.
Yeah,
I do see a little bit of the red.
and I see a little bit of the black.
So I'm with you. I
think it's pretty close for worst. Okay. So let's do one more. Isn't that wild how they're all
that cool?
just right there?
Yeah.
I see just a little bit of color down here in the bottom and at the top.
Yeah. So
I'm going to leave it there, but the main point is that zooming in, all of these are going to, their graphs are all going to look closer and closer to being identical to the tangent line graph, the closer we get to that point of tangency.
So Tom, we've got a great visual here, but you mentioned something else about the table, maybe? Were you going to look at that on the table?
No, I wasn't, but I'd be happy to take a look if you want.
Well, I don't know how valuable it is, and I don't know how distinguishable they are on the table when we're looking at values close to zero and what the delta needs to be or anything like that. If that wasn't something you were going to look at, I don't know that it's worth it. But
So I would point out, though, for the other thing one could do is if you just turn on trace,
yeah,
and let me just move a few pixels over. So I'll go over to.
That's a good idea. Rather than looking at the table, if you just shift over a little bit and then use the up arrow to cycle through them.
Exactly. So here, the quadratics value is 0.997. Then an up arrow. Okay, that's the I should have down arrow, I guess. That's the tangent.
That's the tangent
value.
That's the target, 0.9976. Woo,
oh man, they're all pretty
close.
But you can see a little bit of variation there in those Y values.
Just a
as soon
little.
as we got off the point of tangency, there is a little bit of difference. But boy, but it also kind of drives home just how close these are to each other.
Yeah.
But a table's fine. It takes actually enough time to set it up that I sometimes find the trace is kind of a more direct way.
Yeah, it seems like trace might be a more direct
value.
exploration here. Yep. Yeah.
Numerically even. Yeah. So, all right, I'm going to do a stop share so that.
Okay, Tom, I just got a couple of other things here, Curtis, on our overtime problems.
Okay.
I wanted to show a couple of other things here. So these are from questions that occurred that showed up on the Facebook group. And I wanted to point out a couple of things here. Tom and three of us don't have the opportunity to do many BC problems, but this was actually a BC problem that was posed in the Facebook page. And I wanted to show just a couple of quick things here. This had to do with the volume of a solid of revolution. And the graph, the function, excuse me, is y equal minus the log of x between 0 and 1, okay? So it's actually taking this area and it's revolving it about the x-axis. And this is kind of an odd one because it is an area that has infinite extent because the log of x is not defined at 0. This is minus the log of x, so it's going up to plus infinity. So in fact, here is the setup with pi r squared, okay? For those of you who have done volume and solids of volume of solids of revolution, just want to point out something. I'm going to square it. How do you get from here to here? This is integration by parts. I don't have a problem with that. BC students need to know integration by parts. If they do that on the exam, please make sure they're very careful in their notation, telling us what U is, telling us what DV is. But here's the problem that I have with this particular question. If I find the antiderivative and I plug in the bounds 1 and b, oh, and by the way, don't forget, this is an improper integral. This is an improper integral, so we've got to have this limit out in front. And remember, we carry that limit until we actually evaluate that limit. So the point I want to make, keepers, if I get there, is that right here to this point. Now look, this is the correct answer, which is absolutely amazing, that the volume of that solid is 2 pi. But in this final line right here, there are two limits which students would not be expected to know on the BC. One of them is this. This is the limit as b goes to 0 from the right. I'm going to write it as b times the log of b squared. Now, why is that? Well, that's because as b goes to 0 from the right, this is going to 0. But Curtis, what is this expression going to? Log b squared? That's going to what?
I'm having to think. Log b as we're approaching 0?
It's going to
think big. Think
really big.
Well, I was thinking as we're approaching 0, it's got to be getting very, very large.
Okay, so large negative, squaring it, large positive. So this is increasing without bounds. So this is an indeterminate form of 0 times infinity. Now, students are not expected to know how to do that limit on the exam, although I know many teachers do cover this. And there was another one in here, which is actually 0 times minus infinity. So students, again, aren't expected to know that. You're not going to see this problem on the exam. I wanted to point that out because it was on the Facebook page. Okay, here's another quick one. I won't read through all of this, but this had to do with what is necessary for justification in certain cases. Suppose I wanted to find all those values where a function has a local maximum or a local minimum value. And the question came up about sign charts. So, all right.
Yes.
All right. So here's a function up here. It's a polynomial. I took the derivative. I factor completely. I find the critical values, those places where the derivative is 0 or doesn't exist. In my class, I believe that sign charts are wonderful notation. And I allow my students to draw a sign chart, a well-labeled sign chart, and I have my own notation for local maximum and local minimum. But I allow a student to draw a sign chart and write this conclusion. There is a relative maximum at x equal -1. There's a minimum at x equal 1. What's the justification in my class? The justification is the sign chart. But for the AP exam, that is not sufficient.
Yeah.
Can students draw a sign chart? Absolutely. They don't need one, but they can use one. But they must write something like the following. F has a relative maximum, at x equal -1 because f prime changes from positive to negative there. So they must write something. Now, I've always wondered about this, and we'll leave this for another discussion some evening, Curtis. But if a student is answering this question and they find the derivative and they don't include any sort of sign chart, nothing here, and all of a sudden they write those two conclusions, I always wonder, well, how do they know that? What sort of analysis did they do in order to get it? And
to me, and I put it in the chat too. I think that a sign chart is great to keep yourself organized.
I agree.
And kind of keep, I mean, I love the justification and the sentence that actually explains what the sign chart shows. But to me, writing the sign chart is almost required. Well, it would be for me anyway, to keep my mind straight. I know that.
All right, last one, and we'll let you go for this evening. This was a problem posed on the Facebook page. And here's a function defined piecewise. Looks kind of crazy. There's a trig function in there. There's a rational function in there. And it simply asks for points of discontinuity. Since we've been talking a little bit about differentiability, all right, we might as well talk about some discontinuity points here. Classify each as removable or non-removable. Well, we post these answers, so these will be posted tomorrow. But I produced a graph of this, and it actually has a jump discontinuity over here at 0, and there's actually a vertical asymptote at x equal 2. And so there are two non-removable discontinuities here. What is a removable discontinuity? Well, basically it means if you color in the circle, then you make the graph continuous. You can't do that at either of these points, x equals 0 or x equal 2. So there are two non-removable discontinuities there. Thanks, Curtis, for letting me get those in.
No, those are great.
Excellent.
So I just have a couple of little cleanup things, and that is just to, I put it in the chat already, that if you are a teacher and watched all the way to the end here, you can certainly email me and I will send you a certificate or a link to create a certificate for professional learning. Also, please be aware that we are doing another Monday night calculus session 2 weeks from now, which would be October 16th. So we'll be right back here on the same channel, the same place, and the same time. And then we also are doing a session live for pre-calculus teachers. So if you happen to be a teacher of pre-calculus, we are doing another live session on October the 26th, where Steve, Tom, and I will all be in the same room, sitting behind the same desk. And in working problems. Hopefully maybe then I'll have actually done my homework, and
I'm going to check
up, right. So anyway, I glad that everybody joined us, and we'll see you in 2 weeks. Okay, I think that